Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 25th lecture. And last time we left off talking about pointwise convergence for sequence of functions, and we had left the question open a little bit about what it takes for certain preservations of characteristics for functions in the sequence to have and what their limit function will have. And we had been looking at some examples, and I'd like to continue looking at some examples. And so here was the next example. It says let f sub n of x be equal to x squared over 1 plus x squared to the nth power, where x is a real number, and this is true for n equaling 0, 1, 2, 3, and forever. So we're looking at those sequence of functions, and we consider f of x equaling to the sum as n runs from 0 to infinity of f sub n of x. Of course, which is equal to the sum as n runs from 0 to infinity of x squared over 1 plus x squared raised to the n. We're looking at that sum. Now, first thing I want to note is that f sub n of 0, well, that's always 0. And that's true for all n in our collection running from 0 to infinity. And so what that says is, so this sum of a bunch of zeros would be equal to 0, so that's what f of 0 has to be. Now, for x being different from 0, then the sum as n runs from 0 to infinity of x squared over 1 plus x squared raised to the n. Now, one thing you can see is that this x squared is a constant with comparison to the index of the summation, which is n. So I can rewrite this as x squared times the sum as n runs from 0 to infinity of 1 over 1 plus x squared raised to the n. And you could rewrite that as x squared times the sum as n runs from 0 to infinity of 1 over 1 plus x squared raised to the n. Now, that last summation is looking like a geometric sum. So this is equal to x squared times 1 over, so here's what it would sum to, 1 minus 1 over 1 plus x squared. That's what we get. And so let's simplify this. That's the same thing as x squared. Let's see, common denominator is 1 plus x squared here. We have 1 plus x squared over 1 plus x squared minus 1, so it's just x squared over 1 plus x squared in the bottom. So this would be 1 plus x squared in the top, all over x squared. When x squared would cancel, we're just left with 1 plus x squared. So what f of x is, the sum function, it's equal to 0 if x is 0, and it's equal to 1 plus x squared if x is different from 0. And so what this is an example of, it tells us thus a convergent series of continuous functions may have a discontinuous sum. That is, the f of x was discontinuous at x equals 0. Wonderful. Another example is we let f sub n of x be equal to sine of n times x over the square root of n. And that's where x is a real number and n is equal to 1, 2, 3, forever. So it's a natural number. All right, now, here's what I want us to note. That the limit as n goes to infinity, the f sub n of x that's equal to the limit as n goes to infinity of sine of the quantity n times x over the square root of n. And that's equal to 0. Now, that can be seen in that sine of n times x, that guy's going to bounce in between -1 and 1. And so no matter what that is, when you start dividing it by the square root of n, and as n gets really big, the square root of n gets really big, you're having these numbers that are bounded between -1 and 1 being divided by huge numbers, and that's what makes that go to 0. Okay, this is true for all x element of R. Then, f prime of x, okay, I'm sorry, so I should say what f is. Thus, f sub n of x for these guys, these f sub n's, converge to 0 pointwise. Okay, now, also, f, this is my 0, is what f of x is, so that's the limit function, 0. Now, f prime of x, the limit function's derivative, that's 0. Okay? And that's true for all x element of R. Okay. Now, the f sub n's derivative evaluated x, let's see. So this is a function of x, so 1 over the square root of n is something you just write down, and then the derivative of sine of something, that is cosine of the something, and then you have to take the derivative of the something by the chain rule, and so that's n, and so that's equal to the square root of n times cosine of n times x. So that's the first derivative of f sub n. Okay, now, you look at the limit as n goes to infinity of the square root of n times cosine of the quantity n times x, okay? This derivative. It does not exist, when x is equal to 0. When x is equal to 0, this n times 0 is going to be 0. Cosine of 0 is 1. And so really you're just looking at the square root of n. And as n goes to infinity, it goes to infinity. Okay? Square root of n. Okay. So it does not exist if it equals to infinity, is what we say. Okay, so this is an example. Of a sequence f sub n that converges pointwise to f, but the f sub n primes, the derivatives, don't converge to f prime. That's what this is an example of. Let's look at another example. let f sub n of x be equal to n times x times 1 minus x squared raised to the n. And let's look at it as over the set E, which is composed interval from 0 to 1. And here n is going to equal 1, 2, 3, forever. Natural numbers. Okay, note the limit as n goes to infinity of f sub n of x. Okay, that's going to be the limit as n goes to infinity of n times x times 1 minus x squared raised to the n. That's what we have. Now, so that's the limit we're looking at. It's going to vary depending upon what x is. So we'll start off kind of cases, and we'll think if x equals to 0, if x is equal to 0, then f sub n of x equals to f sub n of 0. And look, you have 0 times something, that's just going to be 0. Okay? So this function when x is equal to 0 is 0. And if x is equal to 1, we get the same result. So f sub n of 1 is equal to 0. So in these cases, the limit as n goes to infinity of the f sub n of x, when x is equal to 0 or 1, we get out 0. Okay, so that's the endpoints for the domain of the f sub n's. Now, if 0 is less than x is less than 1, and the other cases that we could have, okay, then we're looking at the limit as n goes to infinity of n times x times 1 minus x squared raised to the n, which we pull out the x because it's constant with respect to n, and this is what we get. Now, when we look at this, let me back up, I'm sorry. When we look at this part right here, okay, I lost an n, so there should be an n here. So that's a correction that needs to be made. And as n goes to infinity, here's what happens. This part right here is going to the form infinity times, here we're taking some number in between 0 and 1 and subtracting 1 from it. That's a number that's going to be in between 0 and 1, not equal to 0, not equal to 1. And when you start raising it to bigger and bigger powers, that goes to 0. So this is like going towards something that's really huge times something really getting close to 0, and that's an indeterminate limit form, so we've got to do some work with that. So here's what we say. We say, well, that's equal to really x times the limit as n goes to infinity. And the way we'll rewrite this is n over 1 minus x squared raised to the minus n. So it's the exact same problem that we had. I've just rewritten it. This is equal to x times the limit as n goes to infinity. Now, look, this part right here is going to infinity, and this part is going to be going towards infinity in the bottom. And so we use L'Hopital's rule, and so we get 1 over, and this guy's derivative. Okay, now, here we hadn't discussed this before, but by calculus, remember we're taking the derivative with respect to n. What we would get would be, this is like an exponential function, okay? So we write down the function, ln of 1 minus x d squared, and then we have to multiply this by the derivative of this, which would be minus 1. Okay. So that ends up being x, And then I can rewrite this as the limit as n goes to infinity. I pull this other guy to the top. So here it'd be 1 minus x squared raised to the n. We'll put a minus sign out in front of it, and then ln of 1 minus x squared. Now this is some number. The ln of 1 minus x squared for a fixed x. And here, n is going towards infinity, and this guy, what's being raised to n, is some number in between 0 and 1. And so what it goes to is 0. So this equals to x times 0, which equals to 0. Okay. So what we conclude then is the f sub n, is the sequence of functions, converge pointwise to f of x equal to 0. Now, let's look at the interval from 0 to 1 of the f sub n of x dx. Okay? That would be equal to the interval from 0 to 1 of n times x times 1 minus x squared raised to the n dx. Okay? We pull out the n, and here this is x times 1 minus x squared raised to n. So this is dx. This is like we have something raised to a power. To be able to integrate something raised to a power, you have to have the derivative of what's being raised to the power. What's being raised to the power is 1 minus x squared. Or you can integrate it if you have that. Remember, this is from 0 to 1. So I'm looking for an antiderivative, use the fundamental theorem of calculus. Well, the derivative of 1 minus x squared is minus 2x. So I put a minus 2x there. I put a minus 2. To compensate for that insertion, I have to divide by a minus 2. I can pull constants in and out of the interval. And so now we have minus n over 2. And an antiderivative for this guy is 1 minus x squared raised to 1 higher power divided by this new higher power. Okay. And I want to evaluate that from 0 to 1. Okay. Well, when you stick in 0, when you stick in 1, 1 squared is 1, 1 minus 1, that's 0, you're just going to get 0. When you stick in 0 here, what you're going to get is 1 to the n plus 1 power. Remember, I'm sticking in 0 in for x. So that's just 1. And so what I'm going to get is a minus n over 2 times 1 over n plus 1. Okay. So that ends up being n over 2n plus 2. That's what I got. Okay, so the limit as n goes to infinity of the interval from 0 to 1 of the f sub n dx is equal to the limit as n goes to infinity of n over 2n plus 2. Now look, that's infinity over infinity form. We use L'Hopital's rule, we're going to get 1 over 2. And that's what we get. But the interval from 0 to 1 of the limit as n goes to infinity of the f sub n dx. Now remember, the sequence of f sub n converges pointwise to 0. So this is an interval from 0 to 1 of 0 dx. An interval of 0 is 0. That's what we get. So this was an example of a sequence of functions f sub n they converge pointwise to f, but the interval of sub n's, integral of f sub n's, does not converge, but the limit of the integrals of f sub n. Here, I'll write it down this way. But the sequence of the integrals of f sub n's dx does not converge to the integral of f dx. Okay, this was a kind of a substantial example in that it illustrates that you can't pull limits in and out of intervals, not necessarily. Can't always pull limits in and out of intervals. All right. Here's a way of expressing this, that the book does a good job of saying, is the limit, for our previous example, the limit of integrals does not equal the integral of limits. That's what the last example shows. Here's the definition. Pointwise convergence, turns out we're showing, is not strong enough to preserve a lot of the qualities that we want. But here's a definition that might be strong enough. We say that the sequence of functions f sub n converges uniformly on E to a function f, okay, if for every epsilon greater than 0 there is an integer n such that for all n bigger than or equal to this big N, f sub n of x minus f of x inside absolute values will be less than epsilon. Well, inside norm will be less than epsilon of these complex functions. And that's for all x element of E. Okay. The difference between uniform convergence and pointwise convergence is that for pointwise convergence, we get this in. It depends on epsilon and x. Okay, that's what happens. And so for each x, we dig a different n for pointwise. For uniform convergence, what happens is there's some n that works for all x in E. So it's pictorially. If this is the x and y axis, and let's say this is our f, then what happens is we form some band, if you will. I'm trying to make a duplicate here, f, not very good. Now here's another duplicate of f, not very good. Okay? So here, if this is my f in the middle, okay, this width above is epsilon f plus epsilon this width below is epsilon units below f, so f minus epsilon. And what happens is that the f sub n's, they'll be in here. Maybe you jump around, but they'll be in here for all n big enough, and it works for all the x's along the x-axis for which the domain of the f sub n's, the domains of f sub n's. Okay? That's what's happening pictorially for, this is for uniform convergence. Okay? Let's look at a quick example. So consider f sub n of x equal to xn, which we've already looked at. And let's do it on 0 to 1. Okay, now let's make it, 0 to 1, but we include 0 but not 1. Okay, so here's what we're looking at. We sort of looked at this example before. So here's 1. Don't quite get to 1. Not the value 1. We get, that's f sub 1. And then f sub 2 is, x squared. It looks like this. And x sub 3 is a little bit lower, x cubed. It looks like this. And they continue going this way. Now, we note f sub n of x converges pointwise, what I'll say, to f sub x equal to, let's write it down here, equal to 0. But f sub n, the sequence, does not converge uniformly to 0 on 0 to 1. The reason being is, if I put some band about this epsilon units about 0, in between 0 and 1, the f sub n's are always getting outside this band, and no matter how big n I take, they eventually get outside this band for some x. To illustrate that a little bit more details. Okay. To illustrate this with more details, so that this function does not converge uniformly to 0. Okay. We'll let epsilon be equal to 1/2. Okay. Note 1 is going to be greater than hold on just a second. Let's let n be a natural number. Okay. Note we have 1 is less than the n plus 1 root of 1/2, which is going to be greater than 1/2. Okay. So that's what we have. Okay. And so that proves f sub n's of x don't converge uniformly to 0. Okay. So look, why don't they converge uniformly to 0? We have this picture. Okay. What I'm saying is, if you let 1/2 be what your epsilon is about the function 0, okay? Then I can always, no matter what n you give me, no matter what big N you give me, I can go further along in that sequence and find a point in between 0 and 1. That point is the n plus 1 root of 1/2, such that f of that is going to be bigger than 1/2. Okay? That's what we have. So there's that bigger than or equal to. That's what we do. Okay? And that ends the possibility for being within a half a unit of this. We'll just go to that point. That point is the n plus 1 root of 1/2. Okay. All right. Here's another example, and that is if we let f sub n of x be equal to x to the n, and we look at it on 0 to 1/2 closed interval, then the f sub n of x as a sequence of functions converges to 0 on 0 to 1/2, those x values. And the reason being, so if I look at this picture, so we're only going to 1/2. Okay? And so if we look at those functions, remember when we went to 1, it was up here. We had something that looks like this. And if you see, okay, the highest point for each n happens when x is equal to 1/2. So if we can keep these sequence of functions, the 1/2s, at 1/2, within epsilon units of 0, we'll make every x value for those functions be within epsilon units of 0. And that's done because x to the n is less than or equal to 1/2 to the n, and that's for all x element of 0 to 1/2. Okay? That's what happens. And so if you want to know given epsilon, so given epsilon, let me get a little bit more room. Epsilon greater than 0. Oops. So given epsilon greater than 0, what we want is we want for it to be uniformly convergent. We want 1/2 to the n, this would make all the x's, or all the f sub n of x's, to be less than or equal to epsilon. So what n will do that? How far do we have to push along in the sequence to have this happen? Well, that means solving for n, we have ln of 1/2, n times that. We want to be less than or equal to ln of epsilon. We divide both sides by ln of 1/2. ln of 1/2 is a negative number. So what we want is n to be greater than or equal to ln of epsilon, okay, over ln of 1/2. And I know I can get an n bigger than this number, but the Archimedean property. So let n be an integer such that n is bigger than or equal to ln of e over ln of 1/2. And then for all n bigger than or equal to this big N, here's what we'd have. This would translate into x to the n will be less than or equal to 1/2 raised to the n, but that will be less than or equal to epsilon. And that's what it means, that's what's required for uniform convergence. Okay. The next thing we want to look at is a theorem. And this is the Cauchy criterion for uniform convergence. Here's what it says. It says the sequence of functions f sub n, and running from 1 to infinity. Defined on E, converges uniformly on E if and only if for each epsilon greater than 0, there exists an integer big N such that for all m and n bigger than or equal to big N, x element of V implies so for all x element of E, we got f sub n of x minus f sub m of x will be less than or equal to epsilon. Oh, excuse me. This is an if and only if statement. Okay. So here's the proof. Well, suppose f converges uniformly on E. Okay. And let f be the limit function. Let epsilon be greater than 0 be given. So I'm going in the frontwards direction. Then there exists an integer n, okay, such that, this is from the definition of convergence uniformly, such that for all n greater than or equal to this big N, the norm of f sub n of x minus f of x will be less than or equal to epsilon over 2, and that's true for all x element of E. Thus, for all n and m greater than or equal to this big N, the difference in norms of f sub n of x minus f sub m of x is equal to, well, we'll add and subtract f within this norm. So it's f sub n of x minus f of x plus f of x minus f sub m of x, which by the triangle inequality is less than or equal to the norm of f sub n of x minus f of x plus f of x minus f sub m of x. But since n is bigger than big N, and m is bigger than big N, each one of these quantities is less than or equal to epsilon over 2 plus epsilon over 2, which equals to epsilon. And that's the frontward direction, and that's true for every x element of V. Now we need the backwards direction. Here, we suppose that for any epsilon greater than 0, there exists an integer n such that for all n and m bigger than or equal to this big N, that the norm of f sub n of x minus f sub m of x is less than or equal to epsilon, and that's for all x element V. Said in the backwards hypothesis. Then for each x in E, the sequence f sub n of x forms a Cauchy sequence of complex numbers. Okay, Cauchy sequence of numbers, which converges thus for each x element of E, we define f of x to be equal to the limit as n goes to infinity of f sub n of x. Okay, this we're doing for each x. All right, this means that we have really pointwise convergence. Here's what we want to do. We now want to show that the f sub n of x's converge uniformly to f. That's our goal. Okay, so here we let epsilon be greater than 0 be given. Okay. We need a natural number big N such that for all n bigger than or equal to this big N, f sub n of x minus f of x will be less than or equal to epsilon, and that's for all x element of E. By our assumption, for this direction, we have a natural number such that, I'm holding in, such that for all n and m bigger than or equal to n, the norm of f sub n of x minus f sub n, f sub m of x is going to be less than or equal to epsilon. And that's true for all x element b. So what we do is we fix n greater than or equal to this big N, and let m go to infinity. Now, as a claim, the limit as m goes to infinity. Let me write it down here. Claim. The limit as m goes to infinity of f sub n of x minus f sub m of x will be equal to the norm of f sub n of x minus f of x. Okay, I want to prove this claim. And so here's the proof of claim. What we do, we let delta, that's not going to be my positive number, be greater than 0, be given. Okay, so I'm trying to prove a limit. It's a limit of real numbers. We need a natural number k such that for all m bigger than or equal to this natural number k, this norm, the norm of f sub n of x minus f sub m of x minus the norm of f sub n of x minus f sub x will be less than delta. Okay, well note this norm of norms here. This is less than or equal to the norm of the quantities. Let me write it here. F sub n of x minus f of m of x. That guy, and not in norm, but I just put that in parentheses. So this is the big norm out here, right now. Minus the quantity f n of x minus f of x. Which equals to, the ends will cancel. I'm left with the norm of f of x minus f m of x. Okay, that's what I have. And that guy, that's what we're looking at. And so, since the f sub m's of x converge to f of x pointwise, okay. And then for each x in each, okay, then there exists a k, and I'll say k sub x, that's a natural number, such that for all n bigger than, or m bigger than or equal to this k sub x, this guy, f sub x minus f sub m of x, will be less than epsilon. And so that makes this quantity inside f sub x norms less than epsilon. Okay? Okay, so that's the proof of the claim. And then finally, almost through, that's the proof of the claim. The last thing is, since the norm of f sub n of x minus f sub m of x is less than or equal to epsilon for all n and m bigger than or equal to this big N we have, and that's true for all x element b, okay? Then the limit as n goes to infinity of this norm will be less than or equal to epsilon. Okay? And that's for all, that's the limit as m goes to infinity. For all n bigger than or equal to this big N, and for all x element b. Okay? Thus, we know what this limit is. It's f sub n minus f. It's going to be less than or equal to epsilon. And that's true for all n bigger than or equal to this big N, and for all x element b. And so that means that the f sub n's converge uniformly there. That's enough for this lecture. Thank you very much.